Okay, today the topic is parsing, bottom-up parsing. It is for the 6th semester IT as well as CE Computer Engineering. The subject code goes like 16 IT 601, and for CE it is 16 CE 603. Now here, what happens in the bottom-up parsing, and let me explain a brief introduction of this, which is the syntax analyzer, which we have seen in the second phase of the compiler phases. It follows the production rules, which is defined by the means of a CFG, which is a context-free grammar. So the way the rules, the production rules, which are implemented, which we call it a derivation, it divides the parsing into two types, one being the top-down parsing, another being the bottom-up parsing. So basically we have two types of parsing, top-down as well as bottom-up. So top-down parsing, what happens here? When the parser starts constructing the parse tree from the start symbol, which is denoted usually by S, then tries to transform the start symbol to the input symbol, it is called the top-down parsing. So you can imagine like an inverted tree, the root, the leaves being at the bottom, and at the top you get the roots. So here we have recursive descent parsing. It is a common form of top-down parsing. It is called recursive since it uses a recursive procedures in order to process the input stream. Now recursive descent parsing, it suffers from backtracking. Backtracking, what happens in the backtracking is if one derivation of a production fails, the syntax analyzer, it has to restart the process of derivation using different rules of the same production. So this technique may process the input string more than once in order to determine the right production. Now, what happens in the bottom-up parsing? It starts with the input symbols and it tries to construct a parse tree up to the start symbol. So in both ways, we are trying to make a parse tree. We are trying to create a parse tree. So for example, if you have an input string, which is of A plus B into C, where we have the rules, the production rules, which you have it inside the red box, which are of 5 rules. They are also called as grammar. So the grammar which we are going to use out here are 5 lines. Each line is called a production rule. The first being S can have the form E can have the form E plus T, E can have the form E into T, E can have the form T, and lastly we have T can have the form ID. Now we try to start bottom-up parsing on the input. Now A plus B into C, our input stream is A plus B into C. Now we read the input stream and check if any production matches with the input. So the production rules which we are going to use are given inside the red box, and how the parsing is given, how the parsing is done on the input stream is given in the white box. So we have A plus B into C here. Now if you see A can be thought of as identifier, A, B, and C. So all these 3 letters can be thought of as an identifier. So A is ID, B is also ID, and C is also ID. So in the place of A, what can we substitute in the production rule? So we have the last production rule, T can have the form ID. So in the place of ID, if A can take the place of ID, it will be like T can have the form ID. So in the place of A being ID, T can be replaced. This A can be replaced by ID, and which in turn can be replaced with the left side of the production. There is a non-terminal T. So T is put here and plus B into C. Now in the place of T, what can be substituted? We are going to check from the production rules again. So you have E can have the form T. So in the place of T, the non-terminal T, since E can have the form T, production rule is there. So it can be replaced by E, which you see it out here on the 3rd line. So now we have the input stream E plus B into C. Now in the place of B, in the next line, B is ID. So instead of B, we can use the production rule. T can have the form ID again. So this B will be replaced by T, and again this will be remaining as it is. Now if you see E plus T, which you have it out here on the second production rule, E can have the form E plus T. So for in the place of E plus T, E can be replaced. So we're going to replace all this which you have seen out here by the left hand side of the production rule. Now so E plus T becomes E. Now this is C into C. Now in the place of C being ID, C being ID, it can be replaced with the left side of the production rule, the last production rule, which is T can have the form ID. So you're taking here T, so this becomes E into T. Now if you look at the production rules, you will be seeing from the third line, the third production rule says that E can have the form E into T. So this can be substituted by E. Now if you see this E and try to match with the production rule on this red box, you'll be seeing that S can have the form E. Now S is nothing but the start symbol. When it appears, when the letter S appears, it is usually at the first production rule, which denotes that it is a start symbol. So S can have the form E. Now this E can be replaced with the left side of the production rule, which is the S. That means all this parsing, basically it will lead us to the start symbol. That is the rule. Now in bottom-up parsing, it starts from the leaf nodes of a tree and works in upward direction till it reaches the root node. As I have mentioned earlier, you can imagine an inverted tree. The leaf at the bottom and the roots at the top. So you're going to start from the leaf nodes of a tree and you're going to work in upward direction till it reaches the root node. So here we start from a sentence and then we apply the production rules in a reverse manner in order to reach the start symbol. So in bottom-up parsing, we have a general style which is called the shift-reduce parsing. We try to shift down the input symbols and then we try to reduce with the left-hand side of the production rule. Then which is the more general style of shift-reduce parsing is called LR parsing. This LR parsing is having three types of algorithms. The first is SLR parsing, LR parser, LALR parser. Now coming to the shift-reduce parsing. Shift-reduce parsing, it uses two unique steps for bottom-up parsing. These are known as the shift step, and the second step is known as the reduce step. In the shift step, what happens is the shift step refers to the advancement of the input pointer to the next input symbol, which is called the shifted symbol. And this symbol is pushed onto the stack. So the shifted symbol is treated as a single node of the parse tree. So we are going to implement this using a stack. Now if you can imagine a stack being a container by which you're going to keep the things inside the container. So the last one which you have pushed inside the stack, or that container, the last item that you have put inside the stack is going to be the first one which is coming out. So here, how you're going to push the elements onto the stack is by the push operator, by the use of the push. Now in the reduce step, what happens is when the parser finds the complete grammar rule, that means if it has read the whole left hand side as well as the right hand side, and it replaces it using the left hand side, it is known as reduce step, which we have done earlier in the previous slide. This occurs when the top of the stack contains a handle. Now handle, we'll try to give the definition and see what is the handle all about in the next few slides. Now to reduce, in order to reduce, a pop function is going to be used on the stack, which is going to pop off the handle and replaces it with the left hand side non-terminal symbol. So basically in the stack we'll be using two operators. One is for pushing the input symbol onto the stack, another one is for to take out or to reduce or to remove from the stack by using the pop function. Now, LR parser is a non-recursive shift-reduce bottom-up parser. It uses a wide class of CFG, which is also known as context-free grammar, which was done earlier before the lockdown, which makes it the most efficient syntax analysis technique. LR parsers are also known as LRK parsers, where L stands for the left to right scanning of the input stream, and where R stands for the construction of the rightmost derivation in reverse order, and K denotes the number of the look-ahead symbols in order to make our decisions. Now, there are 3 widely used algorithms which are available for in order to construct the LR parser. The first being SLR1, simple LR parser. It works on the smallest class of grammar. It has few number of states. Hence, we need a very small table. And then it is very simple and it is easy to construct. And the second one is LR1 parser. LR parser works on the complete set of LR1 grammar, generates a large table and large number of states, and it is very difficult to construct and it takes slower to construct. LALR1, which stands for look ahead, LR parser, it works on intermediate size of grammar. The number of states which we have is going to be as same as the one which we have in SLR. Now, there are 2 techniques which we are using for the parsing. One is top-down parsers, which you have it in the LL1 as well as recursive descent parsing. We start at the root of the parse tree and grow towards the leaves. Now, here what happens is we pick a production from the grammar and we try to match the input. Now, if we have a bad pick meaning that it does not match. Now, if you have a bad pick, we may need to backtrack. But there are some grammars which are backtrack free, like the predictive parsing. Now, the second type of parsing technique, which is called the bottom-up parsers, which you can see it in LR1 as well as operator precedence parsing. We start at the leaves and grow towards the root. Bottom-up parsers can handle a large class of grammars. Automatic parser generators such as YACC generate the bottom-up parsers. Now let us do a recap of what we have been learning so far. What is the meaning of parsing? The point of parsing, the reason why we have a parsing is in order to construct a derivation. Derivation consists of a series of rewrite steps, like we can have S derives gamma 0, which derives gamma 1, which derives gamma 2, gamma n minus 1, gamma n, which is going to derive the sentence. Now, each gamma I is a sentential form. If gamma contains only terminal symbols, gamma is a sentence in L of G in the language of the grammar. If gamma contains greater than or equal to 1 non-terminals, gamma is a sentential form. Now, coming back to these terminal symbols and the non-terminals, we have already learned in the classes what are the notational conventions of the terminals and the non-terminals. What are the symbols that has to be kept inside the terminals, and what are the terminals that are going to come under the non-terminals. So I'm thinking that I don't have to redo all those things in this class. Now, to get gamma I from gamma I minus 1, we are going to expand some non-terminal A belonging to gamma I minus 1 by using the production. A can have the form beta. Now, we are going to replace the occurrence of A belonging to gamma I minus 1 with beta in order to get gamma I. So in the leftmost derivation, it would be the first non-terminal where A belongs to gamma I minus 1. So today, since this is a class on bottom-up parsing, it will be dealing with what are the techniques that has to be done under bottom-up parsing. So a bottom-up parser, it builds a derivation by working from the input sentence back towards the start symbol. So you have your sentence here. We have the input here, and we are going to try to move back in order to get the start symbol, which is S. Now, if you have to reduce gamma I to gamma I minus 1 in order to match some right-hand side, the right-hand side is beta, with a substring in gamma I, then we replace the beta with its corresponding left hand side, which is A. The left hand side is the non-terminal A. Now I'm just giving here the example for bottom-up parsing. We have the input, which is A, B, B, C, D, E. The goal or the start symbol, the goal out here, which is written here, these are the production rules, or we can say this, the whole thing is a grammar. This grammar consists of 4 production rules. The first one is, this is the start symbol. The start symbol can have the form A, capital A, then capital B, small letter E. Now this is the second production rule. A can have the form A, B, C, or A can have the form B. So the third production rule is A can have the form B. And the fourth production rule, we have B can have the form D. Now, so we are going to build the parse tree in reverse order. So what we do is, the first thing what we do is create the leaf nodes for the terminals in the input stream. So this is the input. So I'm making a node for all the input string, that is A, B, B, C, D, E. Now we build a parse tree in reverse. We create the leaf nodes for all these terminals, which is like this, the input symbol. Now the leaf nodes make up the initial frontier. So this is our initial frontier. So we expand the frontier at each and every step. Now here we scan the input symbol from left to right, from A, B, B, C, D, E. Now we try to match, or the whole of the frontier, everything with the right hand side of a production rule. Now we look for exact matches. We're going to look which one matches with the left side of the production rule. Now if you see here, we apply rule number 3, which is A can have the form B. So the terminal B is an exact match for the right hand side of rule 3. So if you see this third rule, the third production rule, this is A can have the form B. So this one matches exactly with the right hand side of the production. A can have the form B. Now so the frontier, our frontier has changed since we have applied that production. Now ABC, this is the second rule. A can have the form ABC. So this ABC matches with the right hand side of rule 2. So we apply that one to reduce ABC to A. So this A, B, C to A. Now if we could have applied rule 3 again in order to replace the second B in the input stream, also how do we decide how many symbols do we need to look at in order to get back to the start symbol, which is the goal. We have to get back A, B, E. Now here we apply rule 4. Rule 4 says that B can have the form D. So we apply rule 4 in order to reduce D to B. So this is applied here. Now if you see this A, our goal is, this is our goal. Our goal is, in order to get the goal out here, is A and capital B and small e. So have we arrived at our goal? A, capital B and capital E. So A, B, E, it matches the right hand side of rule 1. So the goal symbol is also called the root of the tree, or which we call it the start symbol. So now we can say that it consumes all input, and then we can accept the string since it matches with the start symbol, which is the goal. Now, what kind of derivation did we apply? Reverse the process and look at which non-terminal is expanded first. Now, what we are going to do next is we are going to reverse the process, which we have done right now, and we are going to look at which non-terminal is expanded first or substituted first. Start with the goal symbol or the start symbol at the root. This is the goal, or which we can call it the S. Now our input is A, B, B, C, D, E. Now we apply rule 1. By rule 1, goal says that goal can have the form AABE. So these are all put here, A, B, and E, by applying rule 1. And by applying rule 4, which is B can have the form D, we are getting this leaf again. B can have the form D. Now if you apply rule 2, which says that A can have the form ABC, we have here A can have the form A, B, and C. So we are applying the rule 2 here, so which is highlighted by the red color outline. Now if we apply rule 3 is A can have the form B. So in the place of this A, I can make a note for this A, which is A can have the form B, by applying rule 3. Now what kind of derivation did we apply? Because now we are getting back at the input symbol, which is A, B, B, C, D, E. So here if you read this one, A, B, B, C, D, E. So we are getting back the input symbol in reverse order. So this is like the rightmost derivation in reverse. So bottom-up parsing can be thought of as trying to get the derivation in rightmost order in a reverse way. So this is the first one, the goal. Then this is the second step which we have done, and this is the third step, and lastly this is our fourth step. So always we have gone from the rightmost, replacing the right hand side of the rightmost non-terminal for expanding the rightmost non-terminal every time. So we can say that it is like the rightmost derivation in reverse order. Now the algorithm for bottom-up parsing is we have to repeat all these steps until the frontier has only one symbol, and that symbol is the start symbol or the goal. So what are the steps which needs to be repeated? The first one is examine the frontier from left to right. Examine the input symbol from left to right and find the substring beta in the frontier such that there is a production in the grammar of the form A can have the form beta. If you have a grammar, all the production will be of the form A can have the form beta. A can have the form beta occurs as one step in the rightmost derivation of the sentence, and we are going to replace the beta with A and make A as the parent of each node that make up beta. So all these things has to be repeated until the input symbol has only one symbol, and that symbol is also the start symbol. Now handles, as we'll be talking handles and handles pruning. Now informally, a substring that matches right hand side of the production and whose replacement gives a step in the reverse rightmost derivation is called a handle. Now formally, how we would have explained, a handle is a right sentential form, gamma is a production A can have the form beta, and is in a position of gamma where the string beta may be found and replaced by A in order to produce the previous right sentential form in the rightmost derivation of gamma. So that means if S can have the form alpha A W, W being the string, in the rightmost derivation, and which can have the form alpha beta W, then beta corresponding to the production of A can have the form beta in the position following the alpha is the handle of alpha beta W. Now let us see the example for handles. If you consider this grammar, E can have the form E plus E, E can have the form E into E, E can have the form within parenthesis E, and E can have the form ID. Now in the rightmost derivation, if we try to derive, E derives E plus E, substituting this first rule, and in the rightmost way, which can also derive E plus E into E by substituting this second rule, which is E can have the form E into E. Now all these underlined ones are the handles. So we are using this one in the first step. This is E plus E is the handle, and in the second step, in the second derivation step, E into E is our handle, And for the third one, E plus E, and we are going to give here the substitution of E can have the form ID. E can have the form ID is the fourth production rule, so this ID becomes the handle here. And for the third derivation, E plus ID2 into ID3, so this E is substituted with we can replace with ID2 since we have E can have the form ID. So this is again it will derive ID1 since E can have the form ID is there, so it can be replaced with this, so it becomes ID1 plus ID2 into ID3. So every time the ones that we are substituting is called the handle. So as we have mentioned earlier, what is a let us try to see what is a right sentential form. It is nothing but a sentential form that occurs in a step of the rightmost derivation. A sentence is a sentential form which consists only of terminals. Now the next one which we have is handle pruning. Now in general term, pruning may be to cut away the unwanted parts of a flower or a tree so that they can have a productive growth. So likewise, handle pruning is nothing but to reduce. Now if beta is a handle and A can have the form beta is a production, reducing beta to A in alpha beta W, that is removing the children of A from the Perse tree. So we're going to remove the children of A from the Perse tree. So the rightmost derivation in reverse can be obtained by using handle pruning. Now if W is the sentence of the grammar, then W is equal to gamma n, where gamma n is the nth right sentential form of some but which is yet unknown rightmost derivation. Like this, you have W, and then you are going to get rightmost derivation, and lastly you are going to get back the start symbol. Now what we do is here we start from gamma n, find the handle which is A n can have the form beta n in gamma n, and we replace that beta n in by A of n in order to get gamma n minus 1. And then the next step what we do is we then find the handle A n minus 1 can have the form beta n minus 1 which is in gamma n minus 1, and then we replace that b n minus 1 by a n minus 1 in order to get gamma n minus 1. Now we replace all this step till we get this start symbol S. Now for the example of handle pruning, these are called the right sentential form, and these are the handles, and these are the reducing production. So pruning in the sense that we are going to reduce the production. Now the grammar which are used here is E can have the form E plus E, E can have the form E into E, E can have the form E, and E can have the form ID. Now the input symbol which we have is ID1 plus ID2 into ID3. Now the handle out here is ID1, and the reducing production which we use is E can have the form ID. So for replacing this ID1, we are using E can have the form ID. So E is put here. So E plus ID2 into ID3. Now here the handle will be ID2, as we have here ID2, and the reducing production is E can have the form ID. So we are replacing this ID2 with the left hand side of the production E. So E plus E into ID3. Now in this third step, our handle is ID3. So the reducing production is E can have the form ID. So now we are replacing this ID3 with the left side of the production, which is E. Now E plus E into E. Now what is the handle here? This is the handle E into E. As we'll be using as the reducing production, E can have the form E into E, which is the second production rule in the grammar which we are using. Now, so it will be only E plus E. Now here, E plus E, if you look at this grammar, we have a grammar in the first production rule, E can have the form E plus E. So this E plus E can become E by using the reduction production rule. E can have the form E plus E. So that at last we should get back to the start symbol, which is E. Now a shift-reduce parser is going to function in a way that we are going to get the rightmost derivation in a reverse order. And the production rule or the grammar which we are going to use is here E can have the form E plus T, or E can have the form T. Now the third production rule is T can have the form T into F, or T can have the form F. And the fifth production rule is F can have the form E within parentheses, or F can have the form ID. Now the rightmost derivation of ID plus ID into ID is going to be like this. E derives E plus T, which derives E plus T into F, which derives E plus T into ID by replacing with the left side of the production rule at all the steps, which again derives E plus F into ID. And lastly, we are getting back the input symbol. Now, if you retrace back all this, that means to say that we are doing the rightmost derivation in a reverse order in order to get back to the start symbol, which is E. Now, the rightmost sentential form, which is ID plus ID into ID, the reducing production which we use here is F can have the form ID, so we are replacing here F. And here on the third step, we are using a reducing production. T can have the form F, so we are writing here in the place of E, in the place of F we have T, so it becomes T plus ID into ID. Now in the fourth step, E can have the form T is there, so we are using this reducing production, which thereby getting E out here in the place of T plus ID into ID. So as we have F can have the form ID, we are replacing in the place of ID as F into ID. So this F can be replaced with the left side of the production by T, so T is written here, and last we are getting this ID, and so this ID can be replaced with the left side of the production, which is F and T into F. Now we have a production rule which states that T can have the form T into F. So by replacing with the left side of the production, we have E plus T. Now at last we have E plus T. Now we have the production rule which says that E can have the form E plus T. So in the place of E plus T, we are replacing with this left side of the production. Thereby we are getting E, which is the start symbol. Now handles are the red and underlined in the right sentential form. So all these handles are underlined and it is put in red color. Now the stack implementation of a shift-reduce parsing, we have 4 possible actions of a shift-reduce parser. Now the first action is shift. The next input symbol is shifted onto the top of the stack by using the push. Now the second action is called reduce. Now reduce will replace the handle on top of the stack by the non-terminal. Now the third action is accept. Now out here, if you have reached the action which is called accept, that means it is a successful, we can announce a successful completion of parsing. And then the fourth action is error. The parser discovers a syntax error and it is calling an error recovery routine. So initially our stack will just contain only the end marker, which is a $sign, which indicates that a $sign is the bottom of the stack. Now the end of the input string is also marked by the end marker, which is $. So inside the stack we will have only $. Dollar indicates the bottom of the stack or the end marker, and in the input string we are going to have the W, which is the string, and the $. Now in the stack we have the $, then the input string is ID1 plus ID2 into ID3 followed by the end marker $. Now what action we have to follow here, so that what are the thing that has to be, what is the action which has to be operated on the input in order to push inside the the element from the input onto the stack. So the action is shift. So using the shift action, we are shifting the first symbol of the input string, which is ID1. Now, so you have here in the second step, our stack is containing ID1 now. And so here our input string becomes plus ID2 into ID3, followed by the dollar. And then what is the action that we can operate on this stack? That is reduce action. We are going to reduce by E can have the form ID. So this ID1 can be replaced with the left side of the production, which is E. By the production rule, E can have the form ID. Now our input string remains the same, which is plus ID2 into ID3, followed by the dollar, which is the end marker. Now here, how do I shift down, or how do I push in the elements of the input string onto the stack? By the shift action. So I put here the shift, and then I push inside the operator, which is plus, inside the stack, and then the input string is now ID2 into ID3, followed by the dollar. Now here, if the contents of the stack is only plus, we cannot apply any rule, any production rule. So now what I do again is I shift ID2 onto the stack. So ID2 is here, and our input string will be into ID3, followed by the dollar. And then what I can do is we can reduce this ID2 by the production. E can have the form ID. So you have here the stack contents becomes E plus E. Now here we are still with into ID3 dollar, and so what I do out here is I have to shift this operator, multiplication operator, onto the stack like this. So it is shifted down here, and so I'm ended up with only ID3 in the input. Now I shift down this ID3 onto the stack by the shift operator or by the shift action. Thereby I have now E plus E into ID3. Now here my input string is empty because I'm ended up with only a dollar here, which is the end marker. Now I can reduce, in order to make this ID3 to a non-terminal, I'm reducing by the production rule. E can have the form ID. So I'm applying here. So it becomes E plus E into E. Now there is no more thing, which is no more input symbol here. So again I reduce by E can have the form E into E. So my E into E becomes E here. And then I try to reduce again by E can have the form E plus E here, in order to get the start symbol. The start symbol of the production which we are using was E. Now here, when the stack is having only the start symbol inside it, and when the input symbol is empty, we can announce successful completion of parsing by the action except. So this parser will repeat the cycle until it has detected error, or until the stack contains the start symbol and the input is empty. So now the stack is S being the start symbol. In our case, in our example, it was E was the start symbol, and our input symbol has to have only $sign. So at this point, the parser will halt and it will announce the successful completion of parsing. Now, we can have lots of conflicts during a shift-reduce parsing as well. So the general shift-reduce technique is, if there is no handle on the stack, then we shift. Now if there is a handle, then we reduce. Now however, what happens when there is a choice? What action you have to take in case both shift and reduce are valid? We can call it a shift-reduce conflict. And which rule to use for a reduction if reduction is possible by more than just one production rule, now which we call it a reduce conflict. So conflicts come either because of ambiguous grammars or parsing method is not powerful enough. How do you get ambiguous grammars? If you can draw two parse tree for a grammar, it is called ambiguous. So ambiguous grammars are not required for parsing. Now to continue with the conflicts come either because of ambiguous grammars or parsing method is not powerful enough. There are context-free grammars for which the shift-reduce parsers cannot be used as well. And the stack contents and the next input symbol may not decide the action. So in that case, we call it a shift-reduce conflict. And we can have what is called reduce conflict as well. So if it is a shift-reduce conflict, we say that whether we're going to make a shift operation or whether we're going to make a reduction operation. Now, when it becomes a reduce conflict, the parser cannot decide which of the several reductions to make. So it becomes a reduce conflict. Now, if a shift-reduce parser cannot be used for a grammar, that grammar is called non-LRK grammar. L in the LRK indicates the left to right scanning of the input symbol, and the R in the LRK denotes the rightmost derivation in reverse order, and the K which we have is here, the small k denotes or it indicates the K look ahead, the number of look ahead symbol. Now an ambiguous grammar can never be a LR grammar. Thank you so much.